So in this second proof, we have, again, another claim of induction, because we are summing terms, and the end index could be to whatever term we want. We have to be really cautious to set this up, because we notice the indices start at I equals 0 and go to n minus 1. So if I had chosen n equals 3, that means I'm essentially summing from n equals 3 minus, or I equals 0 to 3 minus 1, which means that my end index would be 2. So that means I would be summing I equals 0, so 3 to the 0 plus 3 to the first plus 3 to the second. So I stop at 1 minus my upper index. So that comes out to, let's see, 3 to the 0 is 1, plus 3 is 4, plus 9 is 13. And we're claiming that that should be the same thing I would get if I took 3 to the n minus 1 divided by 2. So n in this case is 3. Remember, n minus 1 is 2. And if I take the difference and divide it by 2, I get 27 minus 1 is 26, divided by 2 is 13. So it appears to work so far, at least for that particular case. Now, of course, I want to prove that this holds for any value of n, that I could sum, any finite number short of infinity of these terms together, and that this would be a shorthand way of doing it. So we start off again, step 1. We show it for the base case. Well, the base case would be n equals 1. That's the smallest n I could have, because I can't go from I equals 0 to I equals negative 1. It doesn't really make any sense. This is just for positive exponents. So for n equals 1, I'm going to check to see what the sum from I equals 0 to I equals, from I equals 0 to 0 of 3 to the I. Well, that's just going to be the single term, 3 to the 0 power, which is equal to 1. Okay, so that's if I actually sum it up manually. Of course, it's just one term. There's not much being added together there. But I want to check to see if the formula outputs the same value. Otherwise, it's not always right if it doesn't. So I have 3 to the 3 to the 1 minus 1 over 2. I'm checking equality here. 3 to the 1 minus 1 is 2, over 2 is 1, and so I indeed see that for n equals 1, this formula works. So step 2 is the assumption. So assume true for n equals k. So what does that mean? Well, it means that the sum from I equals 0 all the way up to k, so we're replacing n with k, so that means k minus 1, not n minus 1, of 3 raised to the I power is going to be 3 to the k minus 1, minus 1 over here, all divided by 2. Okay, so this is the fact, this is the thing that I want to be able to use. The reason I assume this, other than the idea of the domino effect, is that I now am going to use this algebraic structure to help me in my next case. So I have to prove true for n equals k plus 1 using the fact that we've assumed that the sum from I equals 0 to k minus 1 is equal to 3 to the I is equal to 3 to the k minus 1 over 2. Okay, so that's the thing I have to prove, right? Okay, well, that's the thing I get to use to make the proof. So to prove, what I want to show is that the sum from I equals, that's kind of messy there, from I, let me try that again. So that sum from I equals 0 to n equals k plus 1, so that means I'm going to k plus 1 minus 1, because this is n minus 1, which is basically just the sum from I equals 0 to k, of 3 to the I want to show that that's going to follow the same structure, 3 to the k plus 1 power, so whatever the value of n is, that's what this exponent needs to be, minus 1 over 2. So that's what I have to show. So I'm going to do kind of a similar thing that I did in the last proof. I'm going to rewrite this. I realize that what this will be is 3 to the 0 plus 3 to the first plus ... plus 3 to the k plus the 3 to the k plus 1 term. So, excuse me, I should take this back. This is plus 3 to the k minus 1, and this should be plus 3 to the k, because keep in mind that my upper index, I'm subtracting 1 off. So in this case, I went from I equals 0 to k minus 1 of 3 to the I. What I'm trying to do is to rewrite this expression so that it includes the terms involved in this expression here. So I'm going to do that. So this component right here, that is equal to the sum from I equals 0 to, let's see, k minus 1. So that's just the k minus 1 terms of 3 to the I, plus this extra term, which is 3 to the k power. Alright, so I want to show that this is going to end up equaling that right there, but I've got to get rid of the summation sign, and I know that that summation is equal to 3 raised to the k minus 1 over 2. So because I know that I want my final answer to be in this form, what I'm going to do here is write this as plus 2 times 3 to the k over 2. Alright, so far so good. So what I have is, I'm going to combine these now. I'm going to show that I'm going to get this right hand side, but I've got to do a little bit more work here. So I have, let's see, I have 2 3 to the k's here, and then I have 1 copy of 3 to the k here. So I have a total of 3 3 to the k's, minus a 1 in the numerator, divided by 2. And that right there is 3 to the first times 3 to the k power, which common bases, I can sum the exponents, which is 3 to the k plus 1 minus 1 over 2. And I have just proven that for if n equals k works, that n equals k plus 1 works as well. And therefore my final conclusion is that the sum of the sum of this geometric series, 3 to the I, is in fact more compactly given by taking 3 to the n power minus 1 over 2. And that completes our proof by induction on this particular example. And they're all very similar in terms of how we do this inductive step typically. Sometimes the algebra can get a little bit complicated, but we end up wanting to deconstruct this as a function of our pre-induction step, and then to make a substitution and combine that all, put that all together, and show that it ends up equaling what we would expect it to equal.